Good afternoon and welcome to the 21st annual exhibit of hydrogen and fuel cells and batteries. We've been here for quite some time talking about the most important developments in this field. It's always exciting to see what's new, what's happening. Right now we're going to be talking with Dr. Christopher Hebling, who's Division Director of Fraunhofer-ISE, and we'll be talking about hydrogen production. Please welcome with me Dr. Christopher Hebling.
Good afternoon.
Good afternoon.
Good afternoon.
Christopher, for the people who don't know, I mean, Fraunhofer is such a huge name. Every MP3 player knows what it's all about. But tell us about specifically Fraunhofer-ISE and what you do there.
Thank you. I'm with the Fraunhofer-Institut for Solar Energy Systems based in Freiburg, next to the Black Forest in the south. We're one out of 67 different Fraunhofer institutes. Our focus is, as the title says, the conversion of renewable energy, the storage of renewable energy, and of course the transmission of energy in the most efficient way. We're like 1,200 scientists and engineers and students, and we focus on applied research in the field I mentioned. It's mostly like photovoltaics and solar thermal applications, but also, and which is that's why we're here, very essential now for the next phase of the turnaround of the energy system is hydrogen technology.
Where are you located in Germany? Where's your institute?
Well, Freiburg is in the very southwest of Germany. It's on the border to both France and Switzerland, and the Black Forest is on the other side. So maybe that's even more known in the international public.
Okay. And you focus on, mobile applications and hydrogen production. Where are we going to start? Are we going to start with electrolysis, which has been around for such a long time, and still developments, improvements are happening? Are we going to do with the electrolysis or the mobile applications? What would you like to start with?
Well, I think electrolysis, that's a field we work on for like more than 20 years, because we think, and that has always been our basic thinking, that hydrogen is one of the basic pillars of a solar energy economy, because hydrogen can be produced out of water, obviously. That's why we do PEM water electrolysis. Right, this could be, half of it could be hydrogen. Because with solar energy, so there's always kind of a mismatch between the generation of the energy and the usage by the customers. Not necessarily always, but in many times. So therefore, you always have the more solar energy you have in the grid, the more you need to think about measures to deal with the mismatch of generation and consumption by the consumer. And this bridge can be easily matched by hydrogen.
Now, there's many, here we're talking about energy storage, of course, and there's many people who have many different solutions to this. But this doesn't involve simply solar energy, of course, because any source of electrical energy from the wind turbines or from solar power is going to create this issue for us that the demand is never going to be in sync with the supply. Some people say we should pump water up to a lake on top of a hill. What is the specific advantage of converting, using electrical energy, water into hydrogen? What is the specific advantage over, let's say, a mechanical storage facility like water?
Well, I want to make the case of this year. So the second week of in January this year, we had kind of a high wind, especially in the north. And so we also do a simulation of the power grids. So for that we get all the data from the grid operator. And what we observed, although there were high winds, more like 10 days. So we observed the power generation of wind in the four grids. So after midnight, it went from like 33, 35 gigawatt wind production in the grid. It went down to like 15. And in the early morning, it went up again to like 30. And this happened like 6 days in a row. And so people would think, so why does the wind die down at nighttime? Always after midnight. We know that the sun is not shining. That's what we understand, even as a solar institute, no sun at nighttime. But why does the wind die down after midnight? And so the easy solution is it did not die down. It was the wind turbines were turned out of the wind because the grid could not swallow the power generated in the hours between like 2 and 5 in the morning because there were no consumers. And so the scale was about 20 gigawatt of power was just turned out of the wind. So all those windmills, they were standing still at nighttime, and in the morning they were turned back into the wind. And if you calculate that, because for the wind park operator, they don't care because they get paid for the wind profile. As long as the wind is blowing, and even if no windmill is turning, they get paid for the wind profile. So because it's not their fault that the grid cannot swallow the power when it's operated. And basically the bill is paid by us. Each of the consumer here sitting, because we do it by this incentive system, because the wind power operator, they have a guarantee for 20 years paid by the wind profile, no matter what's behind it, what the grid can swallow. So this is that's happening today, so to speak, and it's not a future scenario. So we lose significant, it's between 500 gigawatt and 1 terawatt we lose every year of power which would have been generated by the wind basically, and which cannot be swallowed by the grid. And this is the starting point to think about, well, what can we do with the power which cannot be swallowed by the grid? And this is the first business case for electrolyzers.
So, of course, you use that energy. People talk about the efficiency, by the way, of electrolysis, and this has been, for me, an interesting and yet a non-issue at the same time. The reason is that if the energy is just being wasted, literally not created because the grid can't swallow it, and if you can store that energy by converting it into hydrogen and then recover that energy, you shouldn't be worried about whether the electrolysis is 60% efficient or 70 or 80% efficient because the energy is being wasted anyway. But there are questions of efficiencies, and particularly there's questions of what do you do with a gigawatt of energy that has been created, used to create hydrogen. Do you store the hydrogen? Do you run it through a PEM cell and create electrical energy on demand? What are the models for what you do once you've used electrolysis to create large quantities of hydrogen?
Right, good point. Well, first of all, we have to distinguish, especially in Germany, we have kind of two zones. One is the northern zone with all the offshore wind parks. And there are only 5 grid lines reaching the land, and so therefore we have this issue at the grid knots where the lines, the grid meets the overall grid of Germany. So there we have the overload situation. In the south, we have predominantly photovoltaics. We have about 1.2 million photovoltaic installations, whereas like 25,000 wind installations. So that gives you a kind of an order of magnitude. And so with photovoltaics in the south, because the sun is shining obviously more on the south, we don't have this issue yet because PV starts with like 1 kilowatt, so it's decentral, it's all over the place. I mean, if you look at the landscape in Bavaria and Baden-Württemberg, we have all these hundreds of thousands, so the grid is not in danger, so to speak, But in the north, we do have this situation now. And so therefore, and the nice coincidence, let's put it this way, is that we can store the hydrogen in basically unlimited quantities if we store it in salt caverns underground. So we have tons of salt caverns which we use for natural gas storage right now. And so over time, I mean, over years, even decades, we can replace the storage of natural gas with the storage of synthetically produced hydrogen from water, from these electrolyzers. And then, of course, we have to look for the first markets. And so you're right with the efficiency. If power is at zero cost, so then the efficiency is not the first parameter, but we have to make sure that the investment costs are high. Roughly, you can say like a kilowatt costs a kilo euro, which means a megawatt and gigawatt. So you can scale it up. So the investment is high, and those hours which I mentioned, like at nighttime when the wind cannot really be integrated into the grid, they're still kind of rare. So based on that, it would not make a business case yet. So therefore, you have to look for the apples which are hanging lowest, and this is mobility sector. Because that's a nice match right now. Another number which is important, you might, most of you be aware of this energy concept of the German government, which is indicating, or as a target has 80% less CO2 emissions as compared to 1990. And if we look at the last 25 years, so from 1990 till 15, as we have now, you can, and if we zoom in all the sectors which emit CO2, like agriculture, production, industry processes, households, and so on. So if we look at all those sectors, they all contributed. Mostly the energy sector, because we have nearly 30% of renewables in the power generation in Germany now, so that it's a very nice contribution. Even agriculture contributed, and households did a lot in terms of insulation and so on. But there's one sector which did not do a bit. And this is mobility. Okay. Because we're in Germany. we like our cars, we like to speed up and whatever. I mean, we're emotionally on the wrong track, I must say. And if you look at the auto shows right now, so of course we walk to the nicest fast cars. So this is Germany, but CO2 reduction in the mobility sector up to now did not happen, which means that the pressure is on. Because if we really want to squeeze all the CO2 emissions from the value we have now down to 80% less till 2050, then of course the mobility sector has also to contribute, and so therefore the pressure is maximum on the mobility sector, and there are only two solutions to bring the power. Of course, the renewable power into battery electric vehicles, which is fine. But we can also transform it into hydrogen and feed the fuel cell cars with that.
And of course, there are hybrids. I've seen again and again that the mixture of batteries and fuel cells in a number of niche applications, forklift trucks, for example, are financially viable right now. It just takes so little time to charge up a fuel cell, and batteries don't like to be drained down to zero. So there are all sorts of niche applications. When we talk about, though, mobility, you're talking about like cars in general here. This is a massive market. And there's all sorts of interesting issues. When is the infrastructure going to exist so that you can tank a fuel cell car? Where does the hydrogen come from? Every time there is a pilot project for a car, you get some journalist writing an article about how the hydrogen was trucked in with the diesel truck. I mean, it happens to everyone. So how do you see the market implementation of mobile applications? When is it going to happen? How is it going to happen? In Japan, we know it already is happening. In certain areas in, for instance, even downtown Berlin, they have a Feinstaub alarm several times during the summer, and then there's the ozone alarm. So basically, according to European legislation, on these days you should not drive a fossil fuel car. We're getting relatively close to that point where the legislation that even already exists is going to make driving cars difficult. Do you see where do you see it starting, though? Because you're talking about like cars in general. This is not like the post truck. If you're talking about reducing by 80% the emissions of the mobile applications right now, how are we going to move towards that mass market?
Well, that's a difficult question. Well, it can only happen if the regulation and legislation is supporting the introduction of this new drivetrain. Because right now, especially the German economy is so dependent on cars, and the margin is so high with the conventional cars, so the car manufacturer, they won't do it, not voluntarily. Let's put it this way. But if the framework, the political framework, and the setting is in such a way that the advantage of like a diesel car with at least 800 kilometers of range, fairly cheap fuel, and no cost for the CO2 emissions, which you do with on your exhaust pipe, then as long as this advantage is not compensated by any kind of incentive system, which has to be guaranteed by the state, then it will take forever. Let's put it this way. But this shift already is happening. So we have, by the end of the year, we'll have like 50 fueling stations, hydrogen fueling stations. We do have the first cars on the streets. The Daimler B-Class and the Toyota Mirai is, the very first prototypes. We still must say the Hyundai 35 is coming. So yes, the first cars are visible. And they work. Like at my institute, we have the B-Class for like 3 years. We engineered a solar hydrogen filling station, the picture of which is at our booth, just here behind the wall. And so we generate our hydrogen by means of photovoltaics and an electrolyzers, and we run three B-Class cars. And we have visitors basically every day from all over the world. And when they see that, okay, PV on the rooftop, electrolyzer and a dispenser, and the cars running, so this is like a modern fairy tale, because never ever a truck came to refill our fueling station because we produce it on site. But back to your question, we have a free market and free customers who decide on whatever reasons for a certain type of mobility. And we have to generate an incentive system that it's not only the early adopters, which just buy the latest and newest, whatever it is, but also for people who think, okay, over the overall the cost of ownership, so it's at least not more expensive as compared to like a diesel car. And this is this gap over the next at least 5 years be bridged by politics and by the legal framework in general.
In terms of larger scale application, you're so intensely involved in this electrolyzer equation. It's part of the whole hydrogen economy. And for me, this is interesting. When we talk about the grid, there are certain areas where you get a critical number of electrically powered cars, and they start to affect how you can structure the grid. You can use them as storage devices. You can operate certain things. This can have a general influence on how the grid itself is structured as we move away, perhaps, towards a decentralized form of energy production, which is feasible when you have sun energy being produced decentrally in various areas in Germany. Do you see the hydrogen-powered cars as part of a storage equation, or is it simply an application?
Well, it's certainly part of the storage equation because just this morning I had a meeting. We talked about a 300 megawatt electrolyzer scenario for the north, for Brandenburg, and so this is relevant for the energy system. I had to say, but battery-driven cars are not part of the energy system because the storage capacity, even of 1 million cars, is neglectable for the overall energy system. So they are important as part of a mobility development over the next decades, especially for the urban mobility, because as you indicated in your first statement, I think more and more the cities come to a they get tighter and tighter with the emissions of their cars in the inner part of the, especially the old parts in Germany of the cities, or London has the same thing. So, and I know of many cities which think about a legal framework that only zero-emission cars are allowed to enter the city center, as an example. So, and also of the communities, and the municipalities, their cars, they are the first to be adopted to zero-emission standards. And for a lot of mobility sectors, only hydrogen can do the job in terms of range, especially the larger cars when you go to like trucks and delivery vans and all that. This will be tough for batteries to meet the demand. But with a fuel cell car or truck, and if you think even further, for ships and even airplanes, so only a fuel, I mean a high energy density fuel can do the job. So therefore, but I think the cities will be the nucleus for the next phase of mobility development, because they can easily say, okay, in the inner part of the city, only emission-free cars are allowed to enter.
We have time for one question from the audience, if there is anyone who does have one question.
Thank you. Would you have an idea how many households exist in Germany that generate the hydrogen from photovoltaics? And how it's going to progress in the very near future if we are going to use hydrogen for mobility?
Well, yes, I have an idea. It's zero. Right now, not a single household is producing hydrogen on its own, because I think it has to trickle down this technology from the large scale. So right now, the first market for PEM electrolyzers is in the megawatt range. We have, if you look around here, we have several companies which offer really off-the-shelf 2 megawatt, 1 megawatt PEM electrolyzers, but also alkaline electrolyzers, so you can purchase it. And but a megawatt is for a household is not quite the right size. So therefore, I think the next phase will be like smaller communities. And we see right now there is a high effort of districts, regions to be 100% on renewables. Like in the Black Forest, we have one, and I mean at several places. You know, a lot of will of the population says, okay, yes, we have a lot of PV. We can set up more wind power stations. Why not having a region defined as a 100% region? Of course, some biomass does help. And for such regions, such megawatt electrolyzers are a perfect match to compensate, you know, the fluctuations of the grid and transform it into a energy-rich gas, which is hydrogen, which again can be transformed into another, for example, power to liquid. Hydrogen plus CO2 can be transformed to methanol and to OMG, which is a diesel substitute, and so on. So I mean, there's a wonderful landscape of things you can do. But what you're indicating with PV and generating hydrogen on a household scale, which would be like 1 to 5 kilowatt electrolyzers. The electrolyzers you can buy, but you need to pressure up to like 350 if you want to have your car at 700 bars. And then at the latest, it doesn't make sense for a household anymore. But on the other hand, I know, and we will work with such companies, there is an interest also from well-known companies to manufacture small-scale electrolyzers, which have an output pressure of like 30 to 50 bars. And at like 50 bars, the energy density is already enough for household applications. So you can store your hydrogen in your basement and convert the hydrogen by means of a fuel cell and bring it back into both. That's important, heat and electricity. And as a combined heat and power situation, then you're beyond like 90% of efficiency. And then it makes total sense because PV is so inexpensive now. In Germany, in the south, I have a 7.5 kilowatt on my rooftop. So I produce for 10 cents per kilowatt. And if I purchase this from the grid, it's 28 cents per kilowatt. So, I mean, if you build a new house, I mean, you have to do PV on your rooftop no matter what. It's cheaper than anything else. And then if you say 10 kilowatt you can produce, and you have 18 cents of margin in between, you know, before you take it out of the grid. And then, of course, there's a business case visible, not yet there, but the 18 cents in between, you can set up like an electrolyzer with storage and a nice fuel cell. And again, it's early adopters are the first markets, which say people who say, okay, I just want to see if I can be 100% energy autonomous, which is possible now more than ever. But what you're saying, how many? As for the moment, no household, but it's getting visible more and more.
That's a wonderful way to sum things up, actually. We've kind of run out of time here, but it's always been the vision of us at the Hydrogen Fuel Cell exhibit to talk about the final goal, which is self-sustaining energy, environmentally sound, decentralized, effective production, and it's almost like consumer autonomy. You are your own manufacturer of energy.
Right.
What could be better? Dr. Christopher Hebling, it's been a pleasure talking to you, Division Director of Fraunhofer-ISE. The booth is C58. I encourage everyone to go and visit. This conversation has been very informative, but it has to be continued, and I hope we'll see you back here next year.
Thank you so much. And
Okay.
please come to my booth. Thank you.
C58, right over there. Thank you, Christopher.
Thanks a lot.
And thank you.